Welcome back. In this module, we discuss LPP in matrix form and some results on the solution of LPP. The objectives of this module are to know the matrix form of a linear programming problem, to familiarize various representations of linear programming problem, to understand terms associated with LPP, to study the properties of the solution of a LPP. LPP in matrix form. In general mathematical programming problem of optimizing f of x subject to the constraints gi of x less than or equal to 0 for I equal to 1, 2, etc. m, x greater than or equal to 0, when the function f of x and the constraints gi of x for I equal to 1, 2, etc. m all are linear, the problem is a linear programming problem, LPP. So, the problem of LPP is to find an optimal minimum or maximum value of a linear function subject to linear constraints as optimize f of x equal to c1 x1 plus c2 x2 plus etc. plus cn xn subject to a11 x1 plus a12 x2 plus etc. plus a1n xn less than or equal to b1, a21 x1 plus a22 x2 plus etc. plus a2n xn less than or equal to b2, etc. am1 x1 plus am2 x2 plus etc. plus amn xn less than or equal to bm, where x1, x2, etc. xn greater than or equal to 0. In matrix form, the LPP can be written as optimize f of x equal to cx subject to ax less than or equal to b, where x greater than or equal to 0, where A equal to the matrix with row a11, a12, etc. a1n, a21, a22, etc. a2n, etc. finally am1, am2, etc. amn. B equal to the row b1, b2, etc. bm transpose. C equal to the row c1, c2, etc. cm. X equal to the row x1, x2, etc. xm transpose. Here Cj's are called the cost coefficients. General linear programming problem. Consider the linear programming problem optimize f of x equal to c1 x1 plus c2 x2 plus etc. plus cn xn subject to a11 x1 plus a12 x2 plus etc. plus a1n xn less than or equal to or greater than or equal to b1, a21 x1 plus a22 x2 plus etc. plus a2n xn less than or equal to or greater than or equal to b2, etc. finally am1 x1 plus am2 x2 plus etc. plus amn xn less than or equal to or greater than or equal to bm, where x1, x2 canonical form of linear programming problem. The general linear programming problem can always be put in the form maximize f of x equal to c1 x1 plus c2 x2 plus etc. plus cn xn subject to a11 x1 plus a12 x2 plus etc. plus a1n xn less than or equal to b1, a21 x1 plus a22 x2 plus etc. plus a2n xn less than or equal to b2, etc. finally am1 x1 plus am2 x2 plus etc. plus amn xn less than or equal to bm, where x1, x2, etc. xn greater than or equal to 0. This form of LPP is known as the canonical form of LPP. The characteristics of this form are: 1. The objective function is of the maximization type. Minimization of a function is equivalent to the maximization of its negative expression. 2. All the constraints are of the less than or equal to type except for the non-negative restrictions. 3. All the variables are non-negative. Any unrestricted variable can be written as the difference of two non-negative variables, slack and surplus variables. A linear constraint of the form summation j from 1 to n a I j x I j less than or equal to b I can be converted into equality by adding a new non-negative variable to the left hand side of the inequality. Such a variable carries a numerical value which is the difference between the right and left hand side of the inequality and is known as a slack variable. In a similar way, the non-negative variable subtracted from LHS of the inequality of the form summation j from 1 to n aij xij greater than or equal to bi, converting it into a equality is called a surplus variable. Standard form of linear programming problem. Using the slack variables x n plus 1, x n plus 2, etc., x n plus m, the optimization problem given in the matrix form can be rewritten into optimize f of x equal to c1 x1 plus c2 x2 plus etc. plus cn xn plus 0 xn plus 1 plus 0 xn plus 2 plus etc. plus 0 xn plus m subject to a11 x1 plus a12 x2 plus etc. plus a1n xn plus xn plus 1 equal to b1, a21 x1 plus a22 x2 plus etc. plus a2n xn plus xn plus 2 equal to b2, etc. am1 x1 plus am2 x2 plus etc. plus amn xn plus xn plus m equal to bm, where xi greater than or equal to 0 for I equal to 1, 2, etc. m plus n. That is to optimize f of x equal to cx subject to ax equal to b, where x greater than or equal to 0, where c equal to the row c1, c2, etc. cn, 0, 0, etc. 0. A is the matrix with row a11, a12, etc. a1n, 1, 0, 0, etc. 0, a21, a22, etc. a2n, 0, 1, 0, etc. 0, etc. finally am1, am2, etc. amn, 0, 0, etc. 1. X equal to the row x1, x2, etc. xn, xn plus 1, etc. xn plus m the transpose, and B equal to the matrix with row b1, b2, etc. bm transpose, where xi greater than or equal to 0 for I equal to 1, 2, etc. m plus n. This form of LPP is called its standard form. The characteristics of this form are: 1. All the constraints are expressed in the form of equations except for the non-negative restrictions. Number 2. The right hand side of each constraint equation is non-negative. Consider a system of m linearly independent equations Ax equal to b for x greater than or equal to 0, where A is the matrix with row a11, a12, etc. a1n, a21, a22, etc. a2n, and etc. finally am1, am2, etc. amn, and B is the matrix b1, b2, etc. bm transpose, and x is the matrix x1, x2, etc. xn transpose. Here we are considering n variables in m, where m less than n equations. A vector x satisfying Ax equal to b and x greater than or equal to 0 is called a feasible solution of the system. In this system of equations, if any of n minus m variables are given the value 0, the remaining system of m equations in m unknown may have a unique solution. This solution along with the assumed zeros is a solution of Ax equal to b. It is called a basic solution. The m variables remaining in the system after n minus m variables have been put equal to 0 are called the basic variables or simply a basis. The rest of the variables may be called non-basic. Since the unique solution of m equations in m variables may also contain zeros, a basic solution contains at least n minus m zeros. If the number of zeros in the basic solution is n minus m, then the solution is called a non-degenerate basic solution, and if it is greater than n minus m, the solution is said to be degenerating. In a basic solution, if all values of xj's are greater than or equal to 0, then the solution is called basic feasible solution. A basic feasible solution which optimizes the objective function f of x is called an optimum solution. Illustration 1. Rewrite the following LPP in its standard form. Maximize f of x equal to 2x1 plus x2 plus 4x3 subject to minus 2x1 plus 4x2 less than or equal to 4, x1 plus 2x2 plus x3 greater than or equal to 5, 2x1 plus 3x3 less than or equal to 2, where x1, x2 greater than or equal to 0 and x3 unrestricted. Solution. It is to introduce slack variables for the first and third constraints. Let the slack variables be x4 and x6. A surplus variable is to be given for the second constraint. Let it be x5. Now the constraints are changed to equations as minus 2x1 plus 4x2 plus x4 equal to 4, x1 plus 2x2 plus x3 minus x5 equal to 5 and 2x1 plus 3x3 plus x6 equal to 2. Here the variable x3 is unrestricted. Let us change it as the difference between two non-negative variables as x3 equal to x3 dash minus x3 double dash. Hence, the problem is to maximize f of x equal to 2x1 plus x2 plus 4 into x3 dash minus x3 double dash subject to minus 2x1 plus 4x2 plus x4 equal to 4, x1 plus 2x2 plus x3 dash minus x3 double dash minus x5 equal to 5 and 2x1 plus 3 into x3 dash minus x3 double dash plus x6 equal to 2, where x1, x2, x3 dash, x3 double dash greater than or equal to 0. Then the standard form of the problem is maximize f of x equal to 2x1 plus x2 plus 4x3 dash minus 4x3 double dash subject to minus 2x1 plus 4x2 plus x4 equal to 4, x1 plus 2x2 plus x3 dash minus x3 double dash minus x5 equal to 5, 2x1 plus 3x3 dash minus 3x3 double dash plus x6 equal to 2 and x1, x2, x3 dash, x3 double dash are greater than or equal to 0. Illustration 2. Obtain all the basic feasible solutions to the set of linearly independent equations x1 plus 2x2 plus 3x3 equal to 4, 2x1 plus x2 plus 5x3 equal to 5. Solution. Here two linearly independent equations x1 plus 2x2 plus 3x3 equal to 4 and 2x1 plus x2 plus 5x3 equal to 5 in three variables are given. Substituting one of the variables as 0, the basic solution can be obtained. Considering the variable x1 equal to 0, the set of equations reduced to 2x1 plus 3x3 equal to 4 and x2 plus 5x3 equal to 5. Solving these equations, we get x2 equal to 5 by 3 and x3 equal to 2 by 3. Considering the variable x2 equal to 0, the set of equations reduced to x1 plus 3x3 equal to 4 and 2x1 plus 5x3 equal to 5. Solving these equations, we get x1 equal to 5 and x3 equal to minus 1. Considering the variable x3 equal to 0, the set of equations reduced to x1 plus 2x2 equal to 4 and 2x1 plus x2 equal to 5. Solving these equations, we get x1 equal to 2 and x2 equal to 1. Hence, the basic solution of the given system of equations are 0, 5 by 3, 2 by 3, 5, 0, minus 1 and 2, 1, 0. Here the first and third basic solutions are feasible. All the basic solutions are non-degenerate. Canonical form of equations. Let x1, x2, etc. xm be a set of basic variables corresponding to a system of equations Ax equal to b. Let it be equation number 1, where A is the matrix with row A11, A12, etc. A1m, A1m plus 1, etc. A1n, A21, A22, etc. a 2m, a 2m plus 1, etc. a 2n, and etc. finally am1, am2, etc. amm, am plus 1, etc. amn, and B is the matrix b1, b2, etc. bm transpose, and X is the matrix x1, x2, etc. xn transpose. Ax equal to B can be written as the matrix a11, a12, etc. a1m, a21, a22, etc. a2m, etc. am1, am2, etc. am into column matrix x1, x2, etc. xm equal to the column matrix b1 minus a1 m plus 1 x m plus 1, etc. minus a1 n xn, b2 minus a2 m plus 1 x m plus 1, etc. minus a2 n xn, etc. bm minus am m plus 1 x m plus 1, etc. minus am n xn. The m by m matrix on the left hand side is non-singular because the basic vectors which are the columns of this matrix are linearly independent. Pre-multiplying both sides by its inverse, we get the column matrix x1, x2, etc. xm equal to the column matrix b1 bar minus a1 m plus 1 bar x m plus 1, etc. minus a1 n bar xn, b2 bar minus a2 m plus 1 bar x m plus 1, etc. minus a2n bar xn, etc. bm bar minus am m plus 1 bar x m plus 1, etc. minus am n bar xn, or x1 plus a1 m plus 1 bar x m plus 1, etc. plus a1 n bar xn equal to b1 bar, x2 plus a2 m plus 1 bar x m plus 1, etc. plus a2 n bar xn equal to b2 bar, etc. finally xm plus am m plus 1 bar x m plus 1, etc. plus am n bar xn equal to bm bar. Let it be equation number 2. Equations 2 which are equivalent to equation 1 are called the canonical form of the equations provided bi bar greater than or equal to 0 for I equal to 1, 2, etc. m. Corresponding to each feasible basis we can get a canonical form and vice versa. The advantage of putting the equations in a canonical form is that the basis and the corresponding basic feasible solution can be immediately known. Since basic feasible solution should have 0 values for non-basic variables, putting x m plus 1 equal to 0, x m plus 2 equal to 0, etc. x m plus n equal to 0 in equations 2, we get the basic feasible solution as b1 bar, comma b2 bar, etc. bm bar, comma 0, 0, etc. 0. Some results on the solution of LPP. Theorem 1. The set SF of all feasible solutions, if not empty, is convex. Proof. Let x1 and x2 be two feasible solutions, then x1 greater than or equal to 0, x2 greater than or equal to 0, and ax1 equal to b and ax2 equal to b. Consider any convex linear combination of x1 and x2. Let x equal to 1 minus lambda x1 plus lambda x2 for 0 less than or equal to lambda less than or equal to 1. Then ax equal to 1 minus lambda ax1 plus lambda ax2, that is equal to 1 minus lambda b plus lambda b, that is equal to b. Therefore, x is also a feasible solution. Thus, the set of all feasible solutions is a convex set. Theorem 2. A basic feasible solution of LPP is a vertex of the convex set of feasible solutions, or equivalently, if a set of vectors p1, p2, etc. pm can be found that are linearly independent such that psi 1 p1 plus psi 2 p2 plus etc. plus psi m pm equal to b, where psi j greater than or equal to 0 for j equal to 1, 2, etc. m, then x psi equal to psi 1, psi 2, etc. psi m 0, 0, etc. 0, which is a basic feasible solution is an extreme point or vertex of SF. Proof. SF be the set of feasible solutions. Clearly, xi equal to psi 1, psi 2, etc. psi m 0, 0, etc. 0 belongs to SF. Suppose that it is not an extreme point, then two points x1 and x2 different from xi exist in SF such that xi equal to 1 minus lambda into x1 plus lambda into x2 for 0 less than lambda less than 1. That is, psi j equal to lambda into xj1 plus 1 minus lambda into xj2 for j equal to 1, 2, etc. m, and 0 equal to lambda into xj1 plus 1 minus lambda into xj2 for j equal to m plus 1, m plus 2, etc. n. Since x1, x2 belongs to SF, xj1, xj2 greater than or equal to 0. Also 0 less than lambda less than 1. Hence, xj1 equal to xj2 equal to 0 for j equal to m plus 1, m plus 2, etc. n. So, x1 equal to x11, x21, etc. xm1 0, 0, etc. 0 transpose, x2 equal to x12, x22, etc. xm2 0, 0, etc. 0 transpose. Since x1, x2 are solutions of Ax equal to b, x11 p1 plus x21 p2 plus etc. plus xm1 pm equal to b, let it be 1, x12 p1 plus x22 p2 plus etc. plus xm2 pm equal to b, let it be number 2. Since x psi belongs to SF, we have psi 1 p1 plus psi 2 p2 plus etc. plus psi m pm equal to b, let it be 3. Equation 3 minus equation 1 implies psi 1 minus x11 p1 plus psi 2 minus x21 p2 plus etc. plus psi m minus xm1 pm equal to 0, let it be equation 4. But p1, p2, etc. pm are by hypothesis linearly independent. Therefore, equation 4 is possible only for psi 1 minus x11 equal to 0, psi 2 minus x21 equal to 0, etc. psi m minus xm1 equal to 0. This implies psi 1 equal to x11, psi 2 equal to x21, etc. psi m equal to xm1 or x psi equal to x1. This is contradicting the assumption. Hence, x psi is an extreme point. Conversely, theorem 3. A vertex of SF is a basic feasible solution. Proof. Let xi equal to psi 1, psi 2, etc. psi n transpose be a vertex of SF. Then, since xi belongs to SF, xi greater than or equal to 0, let R of the psi j's for j equal to 1, 2, etc. n be non-zero, where r less than or equal to n. Since m less than n, either r less than or equal to m or r greater than m. If r less than or equal to m, then xi is obviously a basic feasible solution, and so the theorem holds. If r greater than m, then we may put xi as xi equal to psi 1, psi 2, etc. psi r 0, 0, etc. 0 transpose, where psi j greater than 0 for j equal to 1, 2, etc. r. Since xi is a solution of Ax equal to b, we have psi 1 p1 plus psi 2 p2 plus etc. plus psi r pr equal to b, let it be 1. As r greater than m, the vectors p1, p2, etc. pr are not linearly independent. So, there exists alpha 1, alpha 2, etc. alpha r not all 0 such that alpha 1 p1 plus alpha 2 p2 plus etc. plus alpha r pr equal to 0. Let it be equation 2. Multiplying equation number 2 by c implies c alpha 1 p1 plus c alpha 2 p2 plus etc. plus c alpha r pr equal to 0. Let it be equation 3. Equation number 1 plus equation number 3 implies psi 1 plus C alpha 1 into P1 plus psi 2 plus C alpha 2 into P2 plus etc. plus psi r plus C alpha r into PR equal to B. And equation number 1 minus equation number 3 implies psi 1 minus C alpha 1 into P1 plus psi 2 minus C alpha 2 into P2 plus etc. plus psi r minus C alpha r into PR equal to B. Choose C greater than 0 sufficiently small to make psi j plus or minus C alpha j greater than 0 for j equal to 1, 2, etc. r. Then we can conclude that x1 equal to psi 1 plus C alpha 1, psi 2 plus C alpha 2, etc. psi r plus C alpha r 0, 0, etc. 0 the transpose, and x2 equal to psi 1 minus C alpha 1, psi 2 minus C alpha 2, etc. psi r minus C alpha r 0, 0, etc. 0 the transpose are feasible solutions. We have now three feasible solutions xi, x1, x2 which are related through xi equal to 1 by 2 x1 plus 1 by 2 x2. That is, xi is a convex linear combination of x1 and x2. This means xi is not a vertex, which contradicts our assumption. Hence, R cannot be greater than m, which means xi is a basic feasible solution. Theorem 4. If Sf is non-empty, the objective function f of x has either an unbounded minimum or it is minimum at a vertex of Sf. Proof. There are two cases of Sf. Number 1, Sf is bounded. Number 2, Sf is unbounded. We are considering only the case where Sf is bounded. To prove f of x is minimum at a vertex of Sf. Since Sf is bounded, Sf has vertices and every point of Sf is a convex linear combination of its vertices. Let x1, x2, etc. xp be the vertices of Sf. There is a point x0 belongs to Sf where f of x is minimum. If x0 is a vertex, then nothing to prove. Otherwise, if x0 is not a vertex, x0 can be expressed as a convex linear combination of xr for r equal to 1, 2, etc. p, and so x0 equal to summation r from 1 to p alpha r pr and summation over r alpha r equal to 1 where alpha r greater than or equal to 0. Since f of x is linear, f of x0 equal to f of summation over r alpha r xr, that is equal to summation over r alpha r into f of xr, that is greater than or equal to summation over r alpha r f of xk, that is equal to f of xk, where f of xk is the least of the values f of xr for r equal to 1, 2, etc. p. But by hypothesis, f of x0 less than or equal to f of xk. This implies f of x0 equal to f of xk, which means that f of x is minimum at xk, which is a vertex of Sf. Theorem 5. If f of x is minimum at more than one of the vertices of Sf, then it is minimum at all those points which are the convex linear combinations of these vertices. Proof. Let x1, x2, etc. xk be the vertices of Sf where f of x is minimum. Then f of x1 equal to f of x2 equal to etc. equal to f of xk. Let y be any convex linear combination of these vertices. Then y equal to summation over r from 1 to k beta r xr, where summation over r beta r equal to 1, beta r greater than or equal to 0. And since f of x is linear, f of y equal to f of summation over r beta r xr, that is equal to summation over r beta r into f of xr, that is equal to summation over r beta r f of x1, that is f of x1, which means f of x is minimum at y also. This module discusses the metric representation of LPP. Various forms of LPP are explained. The terms like feasible solution, basic feasible solution, optimal solution, etc. are familiarized. Some theorems in connection with the solution of LPP are also considered.